How you doing? I'm Mr. Rose, and today we're going to talk about 1983. Well, what happened in 1983? We had some key moments. First, this is what men dressed like in 1983. Notice the suspenders and the fun little shirt going on over here. I don't know what that is. Ladies dressed in this fashionable sense, of which I don't think anybody would be caught dead with today in 2020. The world was introduced to two plumbers. We've got Mario and Luigi, though Luigi is not on screen, in the debut of not Super Mario Brothers, but just Mario Brothers, 1983. Fraggle Rock was introduced in 1983, which is an awesome show. And lastly, the mobile telephone. Yes, this was the cell phones that we used in 1983. They cost about $1 billion. They had terrible service, and you were super cool if you had one. I don't know anyone that had one, other than Zach Morris, but that was after 1983. And actually not the last thing, but the most important thing, perhaps, 1983, was the AP Physics question. It was a kinematics question, and that's the question you see here. And that's what we're really going to talk about for the rest of this time. I'd like you to take a moment, look at our question that we're going to solve, excuse me, and do your best to solve it, and then watch me go through. All right, folks, so here we are. Now we're going to look at part A and part B of this question. I have some of the pertinent information written down. For the entire problem, we're given y is equal to 1/2 x squared. Hopefully you can see that. And I wrote down my given information for part A. Vx is equal to some constant c, where x is equal to c times t. Let me just double check that. Where x is equal, that is perfect. Okay, so now what we want to do, part A, they want us to draw the velocity component and the acceleration component of my graph. Well, based on my given information, we know that the velocity in the x direction is constant. That's just here. So that's going to be nice and easy, tangent to my curve. I'm going to draw my velocity vector, label it v. Well, based on my parabolic path, I know there has to be some acceleration. If there has to be some acceleration and the acceleration in the in the x direction is 0, right? If I know ax is equal to 0, that must mean all of my acceleration is in the y direction. So my y component is strictly, I can even label it ay, but that is all of my acceleration, the only acceleration in that direction. So that's part A. Part B is kind of straightforward as well. There are two ways to do part B. Part B was asking to determine the y component of the particle's velocity as a function of x. So now when you see this, you might be thinking calculus and chain rule. As a physics person, I'm not really thinking chain rule. I'm thinking I want to use what they gave me, and I want to use the physics that I know. So they gave me this y equals 1/2 x squared. What am I going to do with that? Well, if I know that x is equal to ct, I have a direct substitution. This is for Roman numeral number 2. I can say that y is equal to 1/2 times c squared t squared. I just threw that right in as a direct substitution. Well, now I'm looking for the velocity. I'm looking for dy dt, right? Because dy dt is my velocity. So I can just say that dy dt is equal to the velocity in the y direction. And how is that helpful? I can easily take this derivative with respect to t. I can probably do this in my head. I know c is a constant, so c squared is a constant. So that stays the same. The derivative dy with respect to t squared is just t. So the t squared, that squared comes down and cancels out. This is just c squared times t. Now, I'm not done because they wanted this in terms of x. They wanted my y velocity in terms of x. So I'm going to expand this out. Now you may see where I'm going. I can say that the velocity in the y direction is c times ct, where given information at the beginning, x is equal to ct, which means my velocity in the y direction is given by some constant c times x. That is Roman numeral 2. Now, Roman numeral 3 asks for the acceleration. We know there's an acceleration in the y direction based on my graph. So Roman numeral 3 asks for my acceleration in the y direction. Well, I know dy dt is velocity. I know acceleration is my derivative of velocity. So I can say my acceleration in the y direction is dv dt. I should put a little y subscript there. And now I don't want to use this. I want to use what I got in terms of t. Why? Because here I can't take a derivative with respect to x when I don't have with respect to t, when I don't have a t component. So I'm going back to what I had, equals c squared t. So what we're really doing is we're going to say the derivative with respect to time of c squared t. That is my acceleration. Well, this, again, is a constant. The derivative of t with respect to t is just 1, which means my acceleration in the y direction is just c squared. That's all we have for, whoop, can't see it, there we go. That's all we have for part A. Let's move on to part B. Okay, so moving on to part B, I recopied the graph, though that's at the bottom of the question. We're going to come back to that later. They tell us it's the same parabola, which means we have the same y equals 1/2 x squared, but this time they tell me vx, or the velocity in the x direction, is equal to c divided by, well, they actually have 1 plus x squared to the 1/2 power. That's the same thing, obviously, as the square root of 1 plus x squared. And now part A, they want us to show that the particle's speed is constant. So that speed word is the most important. Well, if I have an x and a y component of velocity, how do I figure out the magnitude of that velocity, otherwise known as the speed? Well, hopefully you remember that speed, or just the magnitude of the velocity, is the square root of x squared, whoop, that should be vx squared, vx squared plus vy squared. All right, well, right away I have a vx, so I'm going to start by subbing right in. Speed is equal to the square root of, well, vx squared, that's c squared, and that square root is going to go away. So it's going to be c squared divided by 1 plus x. So that is my x component plus my vy squared. Now that vy squared is where we're going to have a little bit of a hang-up, or where we're going to explore this now. Now we know vy is just dy dt. That's the velocity, right? So vy, I know, is the same thing as saying dy dt. And I have an expression y of 1/2 x squared. Well, this y equals 1/2 x squared. If I take the derivative with respect to t, that x is a variable. That's not a constant. So this is an example of a chain rule. So now let's review the chain rule. Remember, the chain rule, dy dt, that is the same thing as me saying dy dx, dy dx times dx dt. So dx dt I know is just my velocity, right? So now I have dy dt, dy dx times dx dt, which is my velocity with respect to time, which is times c over 1 plus x squared. Well, what is dy dx? Hey, dy dx is just x, right? The derivative, 1/2 x squared with respect to x, the 1/2 go away, is just x. So now I have dy over dt equals, and again, this is all getting plugged into my velocity. This is where I started, equals x times c over 1 plus x squared. Now I can plug directly into it oh yeah, there we go, directly into my y velocity. Sorry, that's off screen. So now I can plug directly into my y velocity. I'm just going to go over here so it's all on one page. Speed is equal to the square root c squared plus 1 plus x, plus I've got an x, times, again, that's going to be squared, c squared over 1 plus x squared. I dropped my squared over there. Expand that. And now here we can see I can factor. So you can see here now I have these common. Oh, I dropped a squared, sorry. X squared times, there, that's right. Now you can see I can factor these guys out. So now I have speed equals, this is all in the square root. I can have c squared over 1 plus x squared times, all right, let's do that math right, 1 plus x squared times 1 plus x squared. There we go. That will cancel with that. And I'm left with the speed is equal to the square root of c squared, which is just c. So it was a little bit complicated, but it wasn't absolutely terrible. Just a little bit of understanding of our chain rule. Now for part B of this question, see, part B says on the diagram, show the particle's velocity and acceleration. So now I'm back to my diagram. I know this is constant. So I know by definition that the velocity is tangent to the curve, just like any curve. And this is a curved path. Well, what does that mean? What is a review of a curved path? A curved path means acceleration is pointing centripetally, or to the center of the proposed curve or circle. So my acceleration is going to be not tangent, not straight up in the y direction, but in a direction that if this parabola continued to go and go and go, we'd always have a direction that is towards the center of curvature of that part of our system. So that is all we have for 1983. I'm going to just switch views momentarily. So I know there's been one thing that's bothering you this entire time, and that is, what the heck is Fraggle Rock? So here's your answer. Those are doozers. And there you have it. That was Fraggle Rock. That's all we have. By all means, if you're watching this on YouTube, feel free to like, comment, to subscribe, and you folks will see me next time.